Hello. Today we're going to participate in a contest, global round. I'm glad that there are global rounds after all. I have today, I think, 3 duels. Yeah, I think 3 duels. Probably will not win them all, but we will try. Termax. Let's call Termax. Okay. I asked for 3 modules, so probably there are 3 modules. However, they did not accept, so we don't know. But mentally, I'm prepared for modules. So probably there are around 7 duels, maybe. Some of them are not accepted, but we don't care. So we are in 0.00. I want to go to XY. Positive integer amount of length in the positive direction of either X or Y axis. Each step must have a length strictly greater than the length of the previous one. So if Y is greater than X, then 2 steps. If X is smaller than Y, then it becomes harder. It's usually 3. Okay, so it's very easy. Okay, X, Y, X, Y. X, Y. Are they positive? Yeah, they're positive. So if Y is greater than X, then it's easy. We return 2. If Y is at most X, so if Y is equal to 1, then return -1. I think also if Y equals X, then -1. Yeah, if Y equals X, that means that either they the last step is the greater thing. Let's return -1 if and then return 3. Okay, 2 to 3, 2, 3. 3 to 3. What, 5, 4 is impossible? 5, 4 is impossible. Ah. Like this? Because the first step is positive. What about 6, 4? Is 6, 4 possible? 6, 4 is possible, I think, because we can go... We can go 1, then 4, and then 5. So it is possible. Integer n. Construct an array of length to n. Exactly twice. Distance between the two occurrences of x is a multiple of x. Do they immediately know how to solve that? Ah, yeah, it's notorious maybe. So for example, let's make it for 8. So we need to do 3, 1, 1, 3, 4, 2, something to 4. What? So I can use up all odd numbers if I want. Like this. But even numbers, they need some number in between. Ah, you can do it greedily. Or can you? Well, if we can do it greedily, then at any moment we have 2k elements. And then you can choose two numbers which are equivalent modulo k. But this will take a while. This will take a while to find such a pair. However, with bit set, you can do it quite fast. And so the solution will be in 10 to 5th power squared over 64. I'm not sure about that. I'm not sure about that, to be honest. Not sure about that. probably can do it greedily. Yeah, let's just do it greedily. I think we can do it greedily, yeah. Probably yes. Okay, there is... Okay. Let's try. Okay, so what do we do? We say that we have vi v2 times n. So let's try the following thing. Let's make a set of all. I think we can make VB. Let's make a priority queue. Okay, so what do? We go through all numbers. We go through all numbers. Okay, let's do it with set, I think. Okay, so for int j in q, you cannot do it like this. So for int j in q, so what do? We say that if if q contains k, then good equals true and break. Okay, so after that, we definitely know that j and k are initialized. Then we say that we okay, let's see. Oh, it's actually nice and very easy. What the hell? How did I not notice this solution? This is very easy. And is it fast? It's really fast. Okay. This is stupid that I didn't come up with this solution, but it works. Is it slow? No, it should not be slow. Okay, so we have a string consisting of several ones and zeros, and we want to check if it's possible to so if we have at least so let's look at any group of ones. If we have any group of ones, then whatever these rabbits do, we can make them not jump because they can look here. If that, and then we will decide to make it look here, it doesn't matter. It will still not jump. So the problem is with a rabbit in a single thing. But if there is a rabbit here, then we can pair them up. Like this. So the only problem is if there are two zeros or zero and an end of the string. So if there is no one in these both things, this is a problem. So the criterion probably is like this. So we have an odd number of ones. Here we have zeros, and here we don't have ones. because that means that we cannot pair them up. Yes. That's the only way. So what do we need to do? We need to find all alternating patterns like this. So how do we do that? How can we do that? So let's say that we have a state. We have a state which says began. Began. So last 0, let's say. Okay, let's say ans. Let's make a bool process. Okay, so also we want odd ones equal false. So if C is 0, then we're interested in so if we see 0, and before that it also was 0, then we're interested if something began or something did not begin. So if something began, and anyway we will say okay, last one, let's say. We will say in the end that last one equals C. So if it already began, then if odd one, then answer equals false. We have failed. Otherwise, began equals true, because we saw 2 zeros. And odd 1 equals false. Okay, otherwise, last thing was 1. Then, if it began, then we again if began, then we don't need to do anything, and if it did not, we also don't need to do anything. Okay, that's it. So now let's consider the case when we see a 1. So if last one is false, that means that we have continued the pattern. We say that odd 1 is not odd 1. And probably that's it. However, if the last symbol also was 1, then we say that began equals false. Okay, that is the solution. Let's check that. So no is third and to last. No is the third one and to last. What? 0100 says no. Ah, I mean, good. I'm interested how it should be done properly with some probably some ranges, steady ranges. I'm not familiar very well with it. Where am I? Ah, 144. Very interesting. We take a value which is greater than 0 and appears at least once. We earn 1 point, and each value x is decreased by 1. Okay, if there is only one different value, then it's easy, because we just take this one different value. What if there are two different values? Okay, second always can achieve at least the same amount of points as first by just repeating their move, unless the last move, except the last move here. So second is first minus the number of non-zeros, probably. And that depends on the parity, actually. Visualizer. Wow. Oh my. Vibe coding reached incredible heights. So Alice and Bob just divide the sum of the array between them. The question is how they divide it. Actually, I'm not right, because Alice can move one becomes a 0, and then Bob cannot get this amount of points. And that's the problem. That's a problem. Okay, let's say that each even number does not matter. Because there is an easy strategy. If someone moves into an even number, the second person just goes the same odd number, and we get again an even number. So even numbers, they don't make a difference in the answer. Only odd numbers make a difference. So after the number became even, we can assume that it does not exist. The moment someone touches an even number, the number becomes even, it does not exist, because it does not make a difference in the final answer. This is my thought, this problem. So probably we just take the groups of odd numbers and take them greedily. That's it, I think. I think that's it. We just take the odd groups greedily. Yeah, I think that's a solution. I think that is the solution. Okay, let's go. So VIVN auto xy equals findance v and it is PLL. So we need to find sum and difference of the two players. In the end, we will return s plus d over 2 and s minus d over 2. That will be the answer. So let's first find the sum. For it, we will simply take accumulate v and 0. Numeric? I don't have a numeric or what? Incredible. It's simply incredible how I don't have a numeric in my code. Okay, so what about the difference? For that we need to group numbers by their oddity. Group the odd numbers by their multiplicity. How to do that? Let's make a map int m plus plus mi, then we go vi v viw for int auto xy from mw dot pushback y sort so for odd numbers we subtract them from the difference. And that's it. Three 1 10 9 2016. Ah, so if I is odd, only then we add. Why? Why? Ah, I didn't read the array. Okay, problem E. Given an array of n non-negative integers, we want to answer q independent scenarios. Perform the following operation. It must be I times. Choose an element and increase it by 1. Now I want to maximize the number of bits that equal to 1 in the bitwise OR. So pop count of OR. Okay, for that, it's obvious that we need to find the minimum number of operations to get 0, 1, 2, 3, etc. k ones. That's what we need to do. Okay, how to get at least k ones? In order to get at least k ones, so what do we have? We have a number like 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1. So obviously we need to make this 0, 1. This is because to make this 0, 1, we will have to make a lot more operations of adding 1, which doesn't make sense. Also, it's kind of obvious that we need to do it greedily. It's kind of obvious that we need to do it greedily. Right? Kind of obvious, yes. So, first things first, let's say that we have, so we have NQAB. Great. So, Q lines, Y lines, and your worker still works in this case. Okay. Okay, the solution consists of two parts. First of all, we need to construct array C, which says find means of A, and then we need to find the positions of elements of B in C. So we need to find the first element which is strictly greater than I, which is upper bound I minus C begin minus 1. That's it, probably. Okay, so we need to find means of an array. So how to do it? We need to do it greedily somehow. We need to do it greedily. So first of all, let's find an OR of all these numbers. Okay, if we do at most billion, then all numbers will be at most 2 billion, and that means that The answer is at most 29 in any case. 31? Why 31? How to make 31? 2 billion? $2 billion? It should be 30. Why 31? Ah, that's okay. 2 billion. Okay, the number is at most 2 billion, but in the end it will be okay. 31. Yes. So the answer will be at most 31. In any case, the answer will be at most 31. So first of all, we need to find the OR of all numbers. Okay, after that, the answer is 0. For this number, and we need to go. So the answer will be at most 31. The answer will be at most 31. So we go like this. So we need to find the first bit, of which is 0. Yes, we need to find the first bit, which is 0. So we say that int new1 equals okay, we find, so this digit will need to become, so we need to do while c is at most new1. So while c is at most new1, we will need to fix this. How do we fix? We take the number which is closest to getting this number. I think. Okay, so what do we check? So first of all, AI should not contain this digit. So if it contains this digit, then we continue. Secondly, we need to take otherwise, so we need to take the residue. What is the residue? We need to take 1 to the power c minus AI and 1c minus 1. So this is how many ones we will have to add. So if res is less than residue, then I equals I and residue equals res. After that, we simply say that AI plus equals residue. We also need to say that ans I equals ans I minus 1. And here we say ans I plus equals residue. Okay. After that, we need to recalculate the O. And we do it like this. So quite simple, I think. It should be kind of slow, but n log square n is more or less fine. Yes, it should be kind of fine. Yes. What's wrong with you? I also need to calculate this number. Or C, I mean C, of course. Not, what? Built-in CTZ of this number. That's what I need. What's problem? What's the problem again? 27. And it's so slow? Ah, I want to find leading zero. Yeah, I want to find the leading zero, not the trailing zero. Oh, I hate this. So how do we define C? How do we define C? We take O, we take end with new1 minus 1, maybe plus 1 here. Like this, okay. So we take this, then we want to count leading zeros. Okay, let's call it indicator. So if indicator is 0, then break. Because we have accomplished what we wanted. Otherwise, we count leading zeros and subtract from 31. Zero, zero, zero? No, not right. First of all, let's see how this array looks like. It's quite big. No, that is very bad. -2? Okay. Kinda ugly, but fine. If it passes all the pretests, at least. I'm feeling sus. No? Maybe it's fine. Okay, problem F. Exchange queries. I'm willing to trade on n different items. Permutation that signifies the relative value of the n items. Due to the never-ending updates in the market, traders will often reevaluate their views on the item values. If we given Q queries, swap and one on the permutations, print the number of pairs ij such that the item I is at least as valuable as item j. So basically, we have several tournaments. And we want to find the total number of edges in all strong connectivity components. Okay, that is nice. But not very. Not really. How many tournaments? We have a lot of tournaments. Ah, 2 traders. So there are 2 tournaments. Okay, 2 tournaments is not that crazy. 2 tournaments is fine. 2 tournaments it's kind of fine. Two tournaments is okay. Okay, what do I have in mind? I have in mind that we have like 2 paths. We have two paths. We have 2 paths. Okay, we can assume that we have 2 permutations simply. And I want to look at such prefixes, such that the set of these elements coincides with the set of these elements. So if they coincide, then it's good. So let's compute a Boolean array of size n plus 1, which means if they coincide or not. Then for each pair of such ones, we will add to the answer something like, so here 3 squared minus 1, I think. I is at least valuable, is at least as valuable as j, right? Okay, always each element. Okay, let's take this, for example, thing. Let's take this thing. So here always each element is at least as valuable as all the next elements, so we automatically get n plus 1 over 2. So we're only interested in the left edges, and each such thing, for example, with difference 2, we have here difference 2. It adds... Okay, so this is coincides and this coincides, so we get 1. So we get k minus 1 over 2 for each block of zeros. So we have some blocks of zeros, and we want to sum up all zeros for them. Okay, that makes sense. It can be done with a segment tree. Oh, I don't like segment trees. Because, you know... So I have a segment tree. I have really not written a segment tree in maybe a year. So what do I need? I need XOR on a segment. I need XOR on a segment. I need XOR on a segment and number of zeros. Ah, maybe plus on a segment. Yeah, maybe plus on a segment. Okay, I need XOR or add on a segment and the number of zeros. How do I do that? No, not number of zeros, but this function of zeros. Need this function. Need this strange function. So for each block of zeros, I need to add k plus 1 over 2 for block of zeros. So sum over blocks of zeros, blocks of cats, k plus 1 over 2. This is what I need. Okay, you can do it the other way, even without random. But still, the set of all blocks of zeros. Oh my god, this is some awful segment tree. Okay, so what do I have in mind? I have in mind that we have for each element, for example, element 5, we have the position of 5 here, let's say it's P5, and the position of 5 in the other, it's Q5. That will automatically mean that everything between P5 and Q5 is zeros. So let's do it the other way. Let's say that we are interested in blocks of ones. 1 means that these two prefixes are different, and 0 means that these two prefixes are not different. So that will mean that all these things are greater than zeros. So they are ones. Okay, what do I say then? I will say then that I want to maintain blocks of non-zeros. So I want to sum k over k plus 1 times k plus 1 over 2 over all blocks of non-zeros. This can be done with a segment tree on minimum. Yes, so for each segment, what do we want? I already hate that. I already very much hate that. But we want for each block, we want the minimum. We want the number of greater than minimum elements here. We want the number of greater than minimum elements here. We want sum of k times k minus 1 over 2's over all greater than minimum blocks. Yes, that is what we want. So what do we need? So in the basic segment of length 1, so we have 4 numbers. We have minimum, we have greater than minimum prefix, we have greater than minimum suffix, and we have statistic. So let's call them A, B, C, D. So for this segment, minimum is xi. We also want element, but element can be maintained at the minimum. So it's xi. So minimum prefix, which is greater than minimum, is 0. Minimum suffix greater than minimum suffix is 0, and statistic is also 0. So then we will need to combine two segments, and we can do it. Well, we also need to... Okay. This is quite awful. The awfulest thing is that we need to subtract on the segment. How do we subtract on the segment if I don't have any pushes? I can make a top to bottom segment tree, but we don't like such trees. Okay, let's call it statistic, and we have minimum. Let's make all longs. Okay, minimum. Prefix, suffix, and statistic. So this is our statistic. Also, we want to combine two statistics. Okay, so first of all, let's say that we... Okay, and also we want to Okay, how do we add this thing? So first of all, if we also want length. We also want a length. Yeah, let's pass both lengths. Okay, how do we combine? So if left mn is equal to right mn, then they're same. And then we need to calculate, let's say that we have statans. So if they're equal, then we need to combine. So ans.prefix is left.prefix, ans.suffix is right dot suffix, and ans.start is left.start plus right.start plus what? Plus ans.prefix times left.suffix times right.prefix. Otherwise, for example, minimum is in the right segment. Then ans.prefix is right.prefix plus left length. ans.suffix is equal to a right.suffix, and ans.statistic equals right statistic plus left length times right.prefix. And otherwise, ans.prefix is left.prefix, ans.suffix equals right.suffix plus left.suffix plus right length, and ans.statistic equal left.statistic plus right length times left.suffix. Good. So we can add two segments now. Now we need vector of statistic. Actually, we can make these two ints. But in this case, we will have to be careful here. Okay. Then we can. So what do we need? Which operations do we need? We need to find the statistic. of the whole tree, and we need to just return v0 dot statistic. Right? Also, we need to add on a segment. How to add on a segment? So it's very easy. We need to add on seg vertex 0 n x y val. So vertex x, vertex y, x and y in val. So there are several cases. So if y is at least vx, or x is at least y, then return nothing. Also, if x is at most vx and y is at least vy, then this segment is inside our segment, and we need to do it on the whole segment. Ah, there are pushes also. There are pushes. This is not good. This is not good. Okay, let's also add push. Okay, so we need to make a function push. How do we make a function push? So we need to add something to the children. So first of all, if there are no children, we don't do anything. So otherwise we say vm equals vx plus vy over 2. Int l equals 2 times v plus 1. R equals 2 times v plus 2. And basically we just say that vl plus equals... also, if pv equals 0, then also return. This is crazy. V, I understand what's wrong with V. Okay, let's do it like this. Okay. This is the push operation. Okay, add on segment. So in this case, we simply add it. Let's say that we have an operation of adding something to a vertex. So we say that w v plus equals val and p v plus equals val. this case, we just need to write add to vertex L PV and R PV. Okay, in this case, we need to add to vertex V value val. That's it. Okay, the remaining case is to push to both left and right children, like this. Like this. So left child Vx Vm xy val R Vm Vr xy val, and we need to say that before that we made a push of Vx Vy. We actually don't need Vx and Vy. Okay, let's say that we need them, although we don't need. And we finally need to say that v equals add of VL Vm minus Vx Vr Vy minus Vm. Okay, after that it's almost easy because we have what? We have two initial permutations. Let's say that it is an array vi2. What's wrong with you? So we have an array, and we have no, not find means. I mean, we have some operations, and each operation is bool and two integers. Okay, if we have this, we want to return the number of pairs, which is VL. So let's start with this thing. Okay. I think minus minus AI will be necessary. Then this vector R of size Q Okay, something like this. Okay, let's go. How to solve this nice and easy problem. So again, what does it say? Pi and pj mean the costs. Whereas I thought in terms of not costs, but positions. So let's make a position array. Let's make a position array. So in order to do that, we say that ai.resize n and for int I from 0 j ai j pos I aij equals j. Okay, we have inverted the both arrays. Now we want to create a segment tree of size n. Then we want to for each item we want to construct add once in this tree. Actually, I think it is n+1. Although it's not necessary. The full prefix is always intact. So we don't really need that. Okay, let's say that we have a0 I minimum and the maximum. And we want to add that to the tree. Okay. How did they do it so fast? Okay, I am not the one to judge. So we go through these pairs. What will happen eventually? Eventually, we make a swap. Swap pi and pj. Actually, we don't need the pause, I think, right? We don't need the pause at all. And here it should have been pause. Okay, let's make a special function which adds from something to something. Which adds or removes the position. And it does this. Okay, so here we simply add I1. Here we add -1 to px and py. Then we want to swap a t p.x, a t p.y, and add them back. And then push back tree.find statistic. That's it. Zero, one, one, zero. No. Really no. We need to add something to the answer, of course. So we always need to add the answer n times n plus 1 over 2. So it is automatically added. Okay, let's do this. 3, 3. 3, 3. No, it should be not 3, 3. It should be 3, 4. I understood. So if the minimum is 0, then the statistic. But if the minimum is not 0, then no. Then we need to add something like this. But this doesn't matter, of course. So what does the tree says? So what does the tree say? Okay, I also want to construct a string. How to construct a string? Okay, so if y minus vx equals 1, then answer plus equals to string of wv dot mn. Else we need to push, then we need to add string of 2v plus 1 vx plus vy over 2 answer plus equals string of 2 times v plus 2 vx plus vy over 2 vy. Okay, that is not const. This is also not const. Two zero 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 and then again 2 0. Okay, let's also add the statistics, other statistics. So we need to somehow combine this segment and this segment. And they actually need to be combined. Ah, I understand what has gotten wrong. Because here, when I calculate start, well, actually, I have right start and this, and also I need to take the whole left part as well. So I also need to add left length times left length plus 1 over 2. Here I need this as well. Okay, probably. Okay, let's hide that. Let's hide that at all. And we see 3, 4. Okay, now let's make this 3, 4, 6, 9, 9, 12, 11. This is huge. Such a crappy segment tree. And it took me what? How much? Okay. Okay, 46 minutes on both thinking of it and implementing. Probably almost okay. Modular titration. Oh, titration, I know. It's like a generalization of product from sum and power from product. For positive integer a, we define a recurrence like this. Yeah, it's called titration. We said that the positive integer a is m-iterative if the sequence b stabilizes to 1 modulo m. Okay. That is, there exists n as... Okay, yes. For given m, calculate the density of the m-iterative integers. 0? No, not 0. Do somebody solve this or not? Does. Okay, mathematics. So again, sequence B stabilizes to 1. And this is A is tetrative, right? This makes A is tetrative number modulo M. Okay, let's see. So we have like A to the 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 A, something like this. And it should go to 1, stabilize to 1 modulo M. So for basically this means that A should be equal to 1, right? A should be equal to 1. A is easily just 1 because you need 1 to stabilize to 1. To something. It can be A is 1 modulo M, but actually there is question. Okay, so A is definitely 1 modulo M, but besides that, A to the A to the A to the A should become 1 modular order in Z star M of A. Oh my god. So again, we have written the following thing, that A is good if and only if two things are true. Let's call what is good. We want to say that pair A is M good if and only if two things are true. A is equivalent to 1 modulo M and A is ord Z star M A good. Okay, first of all, what is order of A in this group? Well, if A is equal to 1 modulo M, then it's automatically 1. What? Ah, no, 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 no. It's not true. It's not true. So again, A to this giant power is 1 modulo M. That means that giant power is divisible by order of A in Z M star. What is M? M is product of some numbers. Okay, we will be able to factorize. So we know the prime factorization of A. Okay, basically that means that we know all possible orders of all possible orders. We know all possible orders modulo M. Okay, so this power should be divisible by all these numbers, starting from some point. This is basically equivalent to A containing all primes in ord Z star M A. Basically, A is divisible by prime core of ord Z star M A. So what is the so A is divisible by all prime numbers in ord Z star M A. This is what they are saying to us. Also, A is relatively prime with M. In order for this order to exist. Okay, so first of all, okay, let's choose some residue. Let's choose some residue A star modulo M. Let's choose it. So we sum over A star in Z star of M. Then if order of Z star M of A star is not coprime with M, that is bad. That is automatically bad. So from phi of M, we automatically remove everything related to M. So we take the fact that M and ord Z star M A star is 1. So we take this fact. So assume that this fact is true. Then they're coprime. And then the answer, into the answer we add 1 over so what is the density of such numbers? The density of such numbers is 1 over m because we only take such numbers times core of ord z star m a star. Okay, so we want to find this number 1 over m times the sum of the fact that m is coprime with ord z star of m a star divided by the core itself. Which can be rewritten as this. So 1 over m times sum of over all subsets of primes in order of z star m, but without m. So we take all subsets of primes like this, and we want to divide 1 over, not 1, but product of subset times how many times this subset realizes as some residue. So how to do that? This is not good. But a lot of people solve it. Well, I have some... Well, what? 84 people? Literally no one was here. Now there was a bug. 86 people solved module abstraction. And no one in standings. What's happening with Codeforces? Maybe a lot of people solved G but skipped F? What? What is this? Are you kidding me? Guys. What is this? What is this? This is not funny. What? What is this rainbow of people? I suspect something, okay. I suspect something. Okay, let's continue. So 1 over m times sum of over all subsets of primes in this thing. Number of residues that have this subset over the product of this subset. Okay, this is not very easy, but let's try. Let's take all possible subsets of primes. Let's take all subsets of primes. For example, we want to have P1 times P2 times P5 times P6. We want on exactly these primes. Then in the denominator we will have P1, P2, P5, P6. In the numerator we want to find the number of residues whose order has this core. So whose order has this core. How many? Well, P1 times P2 times P5 times P6, I guess. Or no? They have these primes, but they don't have any other primes. Ah, I know. We need to... So we have some group, multiplicative group of Z star M. How many elements have order which is divisible by only these primes, but divisible by all these primes, but not other primes? Let's start with Let's start with 1. How many numbers don't have anything? Only 1. Okay, next thing. What about P1? What about P1? In case of P1, it's much harder. Let me look at something. Okay, is it true that if I have some residue modular p to the power alpha, then it doesn't matter only residue modulo p matters. Is it true that only residue modulo p matters? So can I replace m with core of m? So I want order of... so interesting. Let's look at it modulo p alpha, p to the power alpha. So its multiplicative group looks like p to the alpha minus 1 z. And that means that the order of almost all numbers, is actually divisible by p, and thus it's bad modulo m, and we have to exclude it. So we can only have numbers which are powers, these powers. This modulo. Right? Because if a number is p alpha minus second power, then its order is divisible by p. No, what did I write? It looks like this. So it should be this power. So automatically I will only look at... Okay, I think that we can do it modular core m. And this will divide it by what we need it to be divided. So, okay. So we basically have several primes. How many primes do we have? Okay, 15 primes, and modulo each prime we have some order. Okay, let's finish this. So I need to find fast what I need to do. So I iterate over all possible subsets of primes. And I add how many times this subset of primes is reached, right? I need to add how many times this subset of primes is reached. Okay, if we take it modulo p, how many times it is reached? It is reached. Okay, what do I need to do? I need to take all primes in number m, leave only one entrance of each of them. Then I need to take the number of. Oh, okay, I need to take P1 minus 1, P2 minus 1, Pk minus 1. These are the orders of these multiplicative groups. Then I need to choose any divisor of each of these numbers. One divisor for each of these numbers. Okay. Also, all these divisors should be coprime with this number. Also okay. What next? Next, I basically multiply them. I say that this is the so how many times the order of element here is exactly d1. Exactly d1. Shit. Exactly d1. Probably it's phi of d1. I'm not sure, but I think it's phi of d1. Is it? Because we need to take d1 but subtract all its divisors. Remove all numbers. Yeah, it's just phi of d1. So I take all phi's, multiply them, and then I divide by the product of core of products. I'm not sure about anything of this. Okay, let's try to write it, but I think it might be as well doomed. Okay, so I need to... I need to do it fast? In 2 seconds, 10,000 tests. Okay, then we need to speed up this, of course. Okay, so we have several numbers, n1, etc., and k. We need to sum over all possible choices of divisors, products of phi of di over core of product of di. We need to somehow simplify this, I think. Okay, what is this function at all? What is this function? Sum over di is divisor on of ni, phi of di divided by core of product of di. Okay, let's look first of all at one number. If we have only one number, n1, what is this? Sum of di of d dividing n? Do I have time at all or not? Okay. Phi of d divided by core of d. What is this? First of all, are we entirely sure that it's the answer? Are we entirely sure that it is the answer? Okay, I think we need to model that. So let's take some modulus. Do we only have modulus, right? Yes, we only... No, what? Ah, yeah, we only have modulus. So what do I want? I want to... iterate over all residues. So let's try to go through all numbers. So if GCD I am is greater than 1, then continue. Else okay, what do I need to do here? I need to say that I consider all I want to consider all what? All I want to find its order modulo m. Let's just do it in linear time. Ah. Actually, I can do it with giant step. I have discrete logarithm. So what do I want? I want okay, again, core of A. A is divisible by core of the order of A. So I want A to be divisible by okay, I want A to be divisible by the core of order. How to find the how to check if A is divisible by the core of order? We want to take LLG equals B, and while G is greater than 1, we want to say do G equals GCD G and A. Okay, again, A, we want A to be divisible by the core of B. How to check that? We need to divide B by all primes of A until we stop being able to. Okay, and we need to return, is it true that B is greater than 1? Equals 1. So if divisible by core, if I it is automatically divisible by core. But we need it to be coprime with M. And then we divide by this core. Oh, how to find the core? Okay, and we want to check, is it true that M should be coprime with order? Otherwise, we add to the answer. This fraction. Okay, let's try and do it. Zeros, only zeros. It's sad. Order is 0? Why order is 0? Order is 0? Of 115? Why? Crazy. This is just crazy. Oh my god. I'm very angry. Okay, the answer is correct. We spent almost half of our, more than half of our time on this, but we now know that it is correct. Okay, now let's do it the next way. What? The next way, so we need to somehow analyze this function. The question is, can I replace m with its core? So everywhere here, I will use just the core. Is it fine or not? Kinda. Unfortunately, this is tail because I spent linear time. Okay, we can try to implement this, but it's still too slow. It's just too slow, I think. Maybe it's not, but I don't think so. Okay, let's first of all find the factorization. Okay. Good. Then we remove all the repetitions in the primes. Then we just want to remove all repetitions in the primes. So let's say that for auto x, y in fact, y equals 1. Okay. What next? Now we want to iterate over all possible divisors of numbers of divisors. Okay, let's just do it somehow because I don't want to go crazy. Okay, we know M big. Now vi orders. Let's go. So let's take fi. Then we want to divide it by all numbers in M big. While M big temp is greater than 1, M big temp is GCD of M big temp and orders dot back, and orders dot back divides equal M big temp. Okay, now it is 1. It is 1, it is 1, it is 1. So in orders there are no primes. If I orders div, let's say, let's say that for orders div dot pushback find divisors of factor of orders dot. Okay, next thing, we want to make the vector of tuples. Initially, it is one tuple of length 1. It's one empty tuple. For const vi there from orders div. So if d.size is at least 2, we create a new VVI TPL. And for int I from d, and for const vi e from tpl l from tpl, we say that e dot push back. I needed to do it the other way. E push back I, then tpll push back e, and then e pop back. And in the end, tpl swap tpll. Okay, now we need to take all these tuples and iterate. And we need to take phi's and cores. Okay, let's try. Is it correct here? TPL. TPL is of size 1 and it is empty. This is very bad. I don't understand what's happening here. Fact is of 1 prime 5. Minus 1. Okay, so it consists of 0 and 2, but why not 4, for example? Why not 4? There should be 4 as well. Orders back is 4. So orders div should consist 1 to 2 2. Okay. I'm really unable to write a simple function. Awful. Okay. Okay, TPL, it's great. So we iterate over all this thing, then what do we do? We try to find products of all phi's. And then we need to divide by core. How to find core? The core. I need to, for that, to find the factorizations. So first of all, so I need to factor I to multiply this by f, and then to core equals fact.merge of core and f. This, and then I say that addend equals product of all phi's, that is addend, and divided by inverse of the core. And then I need to say that ans is sum of ans and addend modulo mod. Crazy. 9 minutes. Probably it's still because when there are very many tests, memory limit? How is it memory limit? These tuples take a lot of space. Well, we can do it without it. We even almost have time. Okay, let's say first of all, if orders div dot back dot size equals 1, then orders div dot back dot pop back. This is the first thing that we can optimize. I'm not sure it will help. So let's get rid of this array, I think. So vi indices orders div dot size. While true, first of all, we need to do this. Okay, so we need to take, instead of D, take to D equals orders div index. What is the TPL? TPL. What is div? What is D? Yes, it's an element of orders div. But then what is TPL? I don't need TPL. Okay, I don't need TPL. So T is one of the tuples. So I need indices II, and to take that in orders div II. Like this? Yes. Yes, I hope so. And then I need to increment my indices. So plus plus indices 0 and int I equals 0, and while I is less than indices dot size, I do the following: plus plus indices I, and if indices I is at least orders div II dot size indices II equals 0 and plus plus II. Else break. And if II is at least indices dot size, then break. So now no memory limit possible, but now it's time limit. Most probably. Because I don't know how to do it more optimally. Okay, it's just till 9, yes. What is this number? I don't know. What is this number? Sum of all phi's of all divisors divided by the cores of these divisors. Just what is this? What is this? It's sum of all subsets of n. What do I need to do? I need to choose. So first of all, in the denominator there is just product of s. In the numerator, we have phi of product of s times what? 1 plus p1 plus etc. plus p1 to the power. Is it just sum of divisors or something like that? Yeah, it would be beautiful, but I don't have time. Maybe -1. So we chose some subset of primes. Okay, that is sad, but we didn't solve the problem. And this is one of the persons who I dueled with. What a pity. Okay, massive cheating problem G is not something that I like. Okay, let me think about finishing this. So, phi of product of S. This is okay. Then what? Let's think about it. So I have all divisors of n which are divisible by p1. What do they look like? They either have p1 or p1 squared or p1 cubed or p1 to the power alpha p1 of n. Okay, therefore this is correct. Yes. Something like this. Okay, now let's put each of the elements of this big product to the corresponding bracket. And then we have p1 to the power. Did I forget how the exponent is denoted? Sorry. Ah, new. Ah, here it is. Okay, new, of course. I forgot the Greek letter. Okay, so new. Okay, sum of product. Sum over S as a subset of this. Pi to the power new n minus 1 divided by pi. Ah, of course, if we have this thing and we want to calculate the product of such things, sum of all such products, then it is simply product of these plus ones. So I needed to take product of pi new n plus pi minus 1 over pi. Oh, I was so close to the solution. I was so close to the solution. Твою мать. Okay, so let's fix the solution. Wait, no, what? No, 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 no. What? Ah, this is only... I only solved the case for one number. Yeah, I only solved the case of one number. This is not enough to solve the general case. Yeah, it's just not enough to solve this for the... Okay, no, 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 no. I didn't solve the problem. We know the function when there is only one number, but when there are two numbers, we don't know what to do. Okay, at least I didn't solve the problem. At least I wasn't too close to solving the problem. Okay, problem A. Let's go through all the problems. So we want to get from 0, 0 to xy. We alternate between going horizontally and going vertically. And also each next step should be strictly greater than all the previous ones. We need to find the minimum number of steps to reach xy. So there are several cases. So the easiest case is when x is greater than y, because of course you can not get there in 0 or 1 steps, because this point cannot be on the same vertical line or on the same horizontal line. So you will need at least 2 steps. So if x is greater than y, then the answer is 2, because you can go here. If x is less than y, then you can go horizontally and then vertically. And that is easy. So the answer is 2. The second case is when we obviously can do it in 3 steps. So the if we want to do it in 3 steps, the most sensible thing to do, it seems, is to go 1 step here, then all the way up here, and then all the way up here to the right. So when can we do this? We can do this if this step is greater than this one, and if this step is greater than this one. That means that y is at least 2, and x, it should be at least y plus 2. 3. So let's look graphically which cases we considered. So if this is y and this is x, then we have considered the case when x is less than y. How does it look like? It looks like this. So it looks like this. These points have been considered in this part of the plane. X is less than y, and we have solved the problem. Also, we have solved the problem is x is at least y plus 2. That is this half plane. So this half plane where x is at least y plus 2 is considered, and this half plane is considered. So we now have 2 narrow lines, this line and this line. So we have only left to consider the cases x equals y and x equals y. Okay, actually it starts here and here. X equals y and x equals y plus 1. And well, basically you can prove that you cannot win in both of these cases. Let's start with the easier one, x equals y. So if you have this broken line and the last step is horizontal, you can prove that x should be greater than y. Why is that? Because this step is greater than this one, this step is greater than this one, and this step is greater than this one, and maybe there is one remaining step. There is one remaining step. And if the last step is vertical, then also vertical steps are greater than horizontal ones, because this is greater than this is greater than this, and this is greater than this. So we know that if last is vertical, then y is greater than x. Sorry. And if last is horizontal, then y, sorry, you didn't see part of my writing. Let me move like this. So, and if last is horizontal, then y is less than x. Therefore, in both of these cases, this is impossible. Now you can actually prove that this is also impossible, because if x equals y plus 1, then this is impossible. You cannot have last vertical step if x is equal to y plus 1, because x is greater than y. Therefore, last step should be horizontal. But in this case, you can actually prove that x is at least y plus 2. Why is that? Because this step is greater than this one, this step is greater than this one, this step is greater than this one. So you have, in these steps, you have at least one inequality of form that some xi is greater than some yi. So the difference in this blue part is at least 1. And also we have the first horizontal step, which is also at least 1. So the total difference is at least the number of horizontal steps. And the number of horizontal steps here will be at least 2. So you see. Therefore, these two cases, you can just say in them that it is impossible. Well, problem B. You're given an integer n. We need to construct an array of length 2n with this conditions. Which are the conditions? We need to construct an array of size 2n such that there are exactly 2 1s, 2 2s, 2 3s, 2 4s, etc. and 2 n's. This is the first condition. And the second condition, that the distance between two numbers I should be equal to I. Should be divisible by I. Okay, this is just a constructive problem. This is just a constructive problem. Actually, you can make the distance between I and I equal to 2I, except for n. So the construction is as follows. So let's take number n. So for it to be easier for you to understand, let's consider n equals 6, for example. It doesn't matter if n is odd or even. Let's take n equals 6. Let's take 6. Around it, we will take 2 1s. And the distance between them is 2. And 2 is divisible by 1. Then we put 2 2s. And the distance between them is 4. And 4 is divisible by 2. Then 2 3s with distance 6. Then 2 4s with the distance 8. And you see that basically, and 5 with the distance 10. So in all of these pairs, the distance is divisible by the number itself. However, we have not put 6. But this is not bad because we can put 6 here. And the distance between 6 and 6 here is exactly 6, which is convenient. I didn't think of it, so I wrote some greedy approach, but outstandingly, the greedy approach does exactly this thing. Well, it puts 6 here, you know, it puts 6 here. But after that, I was very lucky that it goes 5 5, then 4 4, then 3 3, because my implementation of greedy approach was like this. So basically, you can also do it greedily if you want, but this is the construction. Okay, problem C, rabbits. Well, it's a crazy problem. So we have zeros where there are flowers, where there is empty, and 1 where there are flowers. Actually, zeros are important and 1s are not important. So in each 0 there is a rabbit. In each 0 there is a rabbit. And each rabbit wants to jump either to the left or to the right, and you need to direct this rabbit to the left or to the right. However, none of the rabbits should jump there. And the rabbit who looks at some position does not jump in one of 3 cases. First of all, if there is a wall here, so the array ends here, then rabbit will not jump. The second case, if there is also 0 here, also not jump. And the third case, if there is a 0 here, and it looks here. In these 3 cases, the rabbit will not jump. And this rabbit will also not jump. So we need to find out whether you can direct each 0 in this array such that none of them actually jumps. Well, the criterion is as follows. You cannot do it if and only if there is this construction. There is 1 0 1 0 1 0 1 0 1 0 1, where the number of zeros is odd, and here there is either a wall or a 1. Here also wall or 1. So why is that? Well, because if we look at all groups of ones, of zeros, you can prove that if there are at least 2 zeros, then you can just direct them at each other. If there is 1 0 and there is a wall here, also 0 can look here. And if there is a 0 which is surrounded by ones, but here are at least 2 zeros, then you can just direct this 0 here. And this 0 here. But what if there is a 0 here and there are 2 ones here? Then actually, instead of that, you can direct this 0 here and these 2 zeros here. So if there are actually a group of zeros. So first of all, okay, if there is a 0 and there are a couple of ones to the both sides or walls, so either wall or 1 here and here. If there is this situation, the 0 cannot, wherever you direct it, it loses. The same goes for a group of zeros which alternate with ones, and if the group is odd, because in this case you cannot divide them into pairs. But if at one of the sides there is not a problematic 0, for example 0 with another 0 here, then you do not need the parity, because you can start from the other side, from this side. And if you end up with this 0 needing that couple, then this 0, since it's not problematic, you can direct it here. And if this 0 does not have a right couple, then it looks at to the left, and this 0 couples with it to the right. So if there is an alternating sequence of zeros, and at one of the sides there is a non-problematic 0, that is a 0 with a wall or 0 with a 0, etc., then the parity of this sequence does not matter. This sequence can be resolved. So the only case when it is not resolved is when there are an odd number of zeros alternating with ones, and here you have a wall or another one, and here you have a wall or another one. Now the question is how to detect that. If there is such a sequence, you can just find all couples of ones. So let's just consider all zeros. And let's count how many ones here, 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 etc. How many ones there are. Then what you really need is you need a sequence of ones. This 1 means that there is exactly 1 in this sequence. You need a sequence of ones, all maximal sequences of ones by inclusion. And then you need to check whether, first of all, the number of zeros is odd, that is, the number of ones is even. And secondly, the number of ones here and here should be either greater than 1 or exactly 1, but then there is a wall. So you need to detect that, and basically that's it. So it's just some linear algorithm. Okay, problem D, game on array. Okay, I don't have a very strict proof for this problem, but I will explain the motivation. So you have an array A of n positive integers, Alice and Bob alternate turns. Alice goes first, and at each turn, each of the players takes any value which is present in the array and subtracts 1 from all occurrences of this number. And also the player earns 1 point for each occurrence. You can note that, okay, so the question is how to solve this problem. How to find out what is the maximal number of points that each of them can guarantee. You can note that after each operation, the sum of the array is decreased by the number of occurrences of x, but the number of points of some player is increased by the same number. So in the end, the sum of both players' scores, the sum of the scores of both players is equal to the sum of the initial values of the all elements. Therefore, this is something like a game with zero sum. So Alice and Bob trying to, well, it's not a zero sum, it's a constant sum, but still each of the players tries to maximize their score and therefore tries to minimize the score of their opponent. In other terms, if Alice wins A and Bob wins B, and A plus B is S and A minus B is D, then actually you can say that A is equal to S plus D over 2, and B is equal to S minus D over 2, and both number S is constant, you cannot change it. So Alice just tries to maximize D, and Bob tries to minimize D. That is what they're doing. They're trying to maximize and minimize D. Now you can notice that there is a strategy for Alice, something like a strategyoid for Alice, how to do some things. Let me think what I want to say. Well, basically what I want to say is that even numbers don't matter. If any of the players thinks that taking some even number is optimal and getting this amount of points, it becomes some odd number. Then the next player always can take this odd number, since it is at least 1, and get the same amount of points. Basically, this couple of turns did not change D. Not exactly this couple of moves, but each even number, for example 6, Alice took 1 of it and then Bob took 1 of it. Or vice versa, first Bob and then Alice. So this number was decreased by 2 and it did not affect the answer. If you think about it, you can prove that actually any even number does not affect the answer. The moment the number becomes even, it is zero. It is just a zero-sum game. You can think about it. You can say, I mean, Alice cannot win from this number because each time she touches this number, Bob can also touch the same number. She cannot increase D out of some even number. And Bob also cannot win out of some even number because Alice can immediately subtract from the same number. So, therefore, the only thing they can win from is odd numbers. Namely, if Alice has some number, for example 3 7s, she can make them into 3 6s. And you can think that these 3 6s just disappeared. Well, they are present in the array, however, they don't matter because, as I said, they're neutral. Nobody can win any points because of the presence of these 3 6s in the array. They might as well disappear. So, if you think about it in this way, then the move is like this. You take some group of odd numbers and just destroy it. And D is increased by the number of these numbers. So now we have the following problem. You have several odd numbers, several groups. Each person just takes some group of odd numbers equal and destroys it. And gets the number of points equal to the number of odd numbers in this group. Now it's very easy to find the optimal strategy. You just need to get the biggest odd group and destroy it. So each person just takes the biggest odd group and takes it. And that's basically it. Each person takes the biggest odd group and destroys it. And so the solution is as follows. You count for each odd number what is the number of occurrences of it. Now you take these numbers of occurrences. You sort them in non-decreasing order. And then this is added to the D. This is subtracted from D. This is added to D. This is subtracted, etc. Now you know D. S is the sum of all numbers in the array. And this way you can find A and B. Okay, next. Problem E. Okay, this is a greedy problem. How to solve such problems? So you have n non-negative integers, and you consider q scenarios. In the ith scenario, they give you bi coins, and one coin. With one coin, you can increase one element by one. You want to maximize the number of bits that equal to 1 in the bitwise OR of this array. Well, how to always do in such situation? So instead of... So you need monotonicity in this problem. What do I mean by that? If you have f is the function that finds the answer for you, yeah, for example, of array and for number b, it is always less or equal than f of a and b prime if b prime is greater than b. Why is that? Because if you want a bigger number of if you get a bigger number of coins, you can just ignore them, or you can get some big answer. This is called monotonicity. And the second thing that you need to understand is that f of a and b is at most 31 if all numbers in a and b are at most 1 billion. This is because all numbers after the operations are at most 2 times 2 billion. And if all numbers are at most 2 billion, then all the bits. Yeah, since this number is less than 2 to the power 31, in any number that you can have in your array, only the last 30 yeah, the last 31 okay, yeah, the last 31 digits can become ones. Okay, so the answer is at most 31 always. But in this case, since the problem is monotonic, and the answer is at most 31, let's reverse it. Revert it. Instead of that, let's call function g of a and c equals the minimum b. It's called argmin. No, yeah, minimum b such that f of a and b is at least c. So this is your function. Why is this more convenient? Because this function g only has 30 32 values. F of a, g of a0, g of a1, etc., g of a31. Only 32 interesting values. And then if you want to find f of ab, it is likewise just the minimum, the maximum c such that g of ac is at most b. And this can be done with binary search or just with linear search, since the number of c's is at most 32. You can just do it linear search with linear search. But with binary search is also fine. It will be log of 32, even faster. So if you find all values of this function g instead of f, then you can solve the problem. And function g can be done greedily in n log squared n. What do I mean by greedy? So if you have some OR, what's the first digit that you want to fix if you want to maximize the number of ones? Of course, you need to somehow to make this 0 into 1. At least in the process. If you want this 0 to become 1, if you want any 0, for example, this 0 to become 1, the step before that, the number which has this 1 appeared had here 0 and here all 1s. But this automatically means that already this 0 is 1 now. Therefore, instead of that 0, let's just make this 0 1. So always your problem is to make the rightmost 0 into 1. And actually, it can be proven, but I will not prove it, that you can do it greedily. You can find the number in which has the minimum number of steps left to make this 0 into 1. So let's just take all numbers, n numbers, and in O of n time, let's find the number in which this is 0, but this number is maximum. So there is the minimum number of steps left to make this 0, 1. If we do it, then okay, if we do it, then at some moment it becomes 1, 1 and a lot of zeros. This might make the following problem. Now this 0 is 1, but now some of the 1s became zeros. But that is not a problem a lot, because now you can take not the the rightmost 0, but the leftmost 0 in this part. Let's take the leftmost 0 in this part and fix it. We can again do it greedily in O of n time. Again, this might become 1, but some 1s became zeros. Not a trouble. Again, we take the leftmost 0 in this part and make it a 1 in O of n time. So you make one fix in O of n time. However, this fix becomes a cascade of fixes, where each digit is fixed at most once. So therefore, in total, there are log n fixes for each digit. And there are at most log n digits which you need to fix. Not log n, but log c, where c is 1 billion. And therefore, n log squared c is the total complexity, which is fine. So greedily find the rightmost 0. Remember its position. And say that now you are going to fix all these suffix. Make it 1, and at some moments, some of the other ones might become zeros. But the position of the leftmost 0 now in this zone only moves to the right. So now you take this 0 and fix it. Now you take this or this if it becomes a 0, 0, and also fix it. So this cascade takes logarithmic time times O of n on one fix. And then in total, the number of such zeros is also logarithmic, so you get this complexity. Okay, and problem F, because problem G was not solved by me. Exchange queries. So basically, the problem is as follows. You have a tournament. It's a sorted tournament. Okay, you just have two permutations. You have two permutations. Of same length. You want to count the number of pairs of indices, for example, 3, 6, such that you can go from 3 to 6 let me think. Yeah. You want to go from 3 to 6 in the following way. You can change 3. So if you have some index, then you can change it to any index j such that pi is greater than pj or qi is greater than qj, at least. Then again, you can change j to k, where at least one of these inequalities holds, and you want to get from 3 to 6. So if it is possible, then 3 to 6 is called a good pair. You need to find the number of good pairs. So this is the problem. So I will temporarily look at the inverse permutations. So here, pi is the cost of ith element in the eyes of the first merchant. Instead of that, let's look at the inverse permutations. In the final answer, in the final solution, they will not be present, but still. Let's say pos 1 and pos 2. So what is pos 1? This is just the order of all the elements from the least popular to the most popular, according to the first merchant. And pos 2 is the order of the elements if we consider the opinion of the second merchant. Then the path from 3 to 6 is as follows. We find 3 in any of these arrays, for example, here, as the value, not as the index of the array, but as the value of the array, and replace it with this one. For example, here we had 3, and here we had 7. Then we again find 7, for example, here, and we go 4. And here, for example, we have 4, and we go to 6. So immediately we could not go from 3 to 6 here because it is to the right. But if we interchangeably use both arrays, then at some moment we can get to the right, more right position than we were before. The question is how many such pairs? Well, actually this problem is a graph theory problem, because basically you have a graph, a directed graph, which looks like a union of two paths, of two Hamiltonian paths. So this is a Hamiltonian path 1, and this is Hamiltonian path 2. So this is a directed graph. And you want to find the number of pairs of vertices I and j such that there is a path from I to j. Well, such pairs are simply such pairs are just reachability in this graph. But what I want to say? I want to say that in such problems, it is important to consider strong connectivity components. So let's just say that two elements are in the same strong connectivity component if you can get from the first one to the second one and from the second one to the first one using only these edges. Then you can have some components. Because this relation, as I said, is an equivalency relation. Also, it looks like this. So if you look at this graph as a condensed graph, where you forget about the fact that there are several vertices here, you consider it as a one big vertex, and this is a one big vertex. And you say that there is an edge here, if and only if at least one pair between these two vertices, mega vertices, has an edge. Then this big condensed graph looks like this. It's just a Hamiltonian path in the condensation. Why is that? This is because this fact is induced by any of these Hamiltonian paths. Since this is Hamiltonian path, that means that there is an order of the vertices in which you can order them, and all the previous vertices, from them, all the later vertices are reachable. That means that you cannot have for example, a vertex from one big mega vertex, then from the other, and then again from this one. Because that would mean that you can get from this vertex to this vertex, and then from this vertex to this vertex. But this means that they are actually in the same connected component, and we should have merged these two vertices, mega vertices. So actually the only way it can look like is in this topological sort, you firstly have all the vertices from some mega vertex, then its child vertex is fully listed, then the next one, the next one, the next one, and the next one. And the same for the second path. So each of these paths is just topological sorting, not only of the initial graph, but of the condensed graph. So how, if this is true, so first of all, which pairs do we want to consider? Basically, so the graph, as I said, looks like this. So I mean, any of the paths. For example, pos 1, how does it look like? So we have our condensed graph. Let me arrange it horizontally. So this is the first condensed vertex, this is the second one, the third one, the fourth one. So it looks like this. We order the vertices in the first condensed vertex in some order. Then we transition to the next vertex. And again, go in some order. And then to the next one in some order. And again. So the question is, how many pairs of reachable vertices are there in this graph? Well, always any edge that looks to the right is a reachability. Simply because, or to the left, but doesn't matter. Let's imagine that to the right. Simply because in pos 1 you can go from this vertex to this vertex. So if we look like this, it's just pairs of vertices that go along the arrows. So which pairs of vertices that don't go along the arrows are there? You cannot go from this vertex to this vertex because they are in different connected, strongly connected components. However, if they are in the same component, then you can get from this to this simply because they are in the same component. Therefore, the answer is the number of edges here, which is n plus 1 over 2. Notice that you can get from the vertex to itself even in this array. Plus the number of ways to go backwards. Number of ways to go backwards in this, for example, strongly connected component is the size times size minus 1 over 2. Yeah, because if you add all the backwards edges, it's the same way, is the same number as the straight edges, and number of both of them is s times s minus 1 over 2. So you want to add to this number sum of these numbers over all strongly connected components. So now the question is, what are the sizes of strongly connected components? Well, in that you can use the second array as an assistance. Let's just look at these two arrays. Where do these first three mega vertices end? If there are S1, S2, and S3 vertices, then the first S1 is the first mega vertex in both arrays, then in both of them S2, and in both of them S3. Therefore, this is just the same set. So you can characterize the position where each mega vertex description ended as the position where these two sets coincide. This is actually not only a property, but it is also a criterion, because if, let's look at in the opposite direction, if we have two subsets here which coincide, this immediately mean that none of these vertices and these vertices are in the same mega vertex. Because yes, you can get from here to here, but you will never be able to get from this vertex to any vertex outside of this set. Because if you use this first permutation, you still end up here. And if you use the second permutation, you also end up here. So you just cannot leave this suffix. Therefore, you just need all positions where the prefix coincides with the prefix. You just need all such positions. Well, how can the prefix not coincide with the prefix? For that, you just need to look at the initial two arrays. And you can note that, for example, if P5 is greater than Q5, yeah, that means that in the array pos, we have number 5 here, but we have number 5 here. And that means that none of these prefix, this prefix, this prefix, etc., this prefix, none of them can coincide. Because if they coincide, that would mean that we have 5 in this prefix, but not in this prefix. That is a contradiction. So I mean, you cannot make this separation line between these two 5s. That is what I want to say. You can move it either to the right of both 5s or to the left of both 5s. Let's formulate it like this. Let's make an auxiliary array, and if we have two numbers which are in different positions, for example here and here, then we add 1 to all these positions in this auxiliary array. This 1 means that there is one obstacle to putting the separation line in this place. For example, if we have now two 6s here and here, we make these two 1s 2s, etc. So for each element, if there are two positions where it is located different, let's add 1 to the corresponding places in this auxiliary array. Okay, so 0 means that we can make a separation here. So zeros are exactly the places where the current strongly connected component ended and the new one started. So if you have two consecutive zeros, maybe two zeros between which there are no other zeros, these are the markers of two strongly connected components. And the size of strongly connected component is this number. So if this is S, let's call this number K, which is the size of non-zero block. Then if you need to add S times S minus 1 over 2 to the answer, it is equivalent to adding K times K plus 1 over 2 to the answer. So the question is, take the auxiliary array and sum this number over all non-zero blocks. This is what you need to do. This is a quite standard problem that can be done with segment tree. So let's just divide it into segments as in the segment tree. And let's understand what we need to find this value. So for example, of course, we need to find this value for the array itself. Yes? So we need to find this value for the array itself. K times K plus 1 over 2, sum over all blocks. So this is the answer for this block. Now let's take another block. How can we merge these two blocks? There is a problem with merging these two blocks, because now what is the answer? The answer is the answer of this block plus the answer of this block plus some modification which is required because there is some block here. On the conjunction of these two blocks. Yes, what do we need to add? So we have added k prime times k prime plus 1 over 2 and k prime prime times k prime prime plus 1 over 2. The sum of these numbers is k prime prime plus k prime prime squared plus k prime squared over 2. But what do we need to have here? Actually, we need to have here k prime plus k prime prime times k prime plus k prime prime plus 1 over 2, which is exactly this plus k prime prime, if you resolve these brackets. So we need to add k prime prime. So we need to know the number of non-zero elements at the suffix of this array and the non-zero elements on the prefix of this array. Okay? So now we need three numbers. We need answer, non-zero suffix, and non-zero prefix. But wait, now we have more issues, because now we need to find the size of non-zero suffix of this whole number. If you want it, how the induction works, if you want something from your children, then you also need to learn how to provide it yourself. Well, now it's kind of easy. If you have at least one zero in this array, this is equivalent to right.suf is less than right.len. And len, you can assume that it is maintained outside of the segment tree, not inside the vertex, so we don't need a special entry for it. So if r.suf is less than r.len, then it is just r.suf. But if r.suf is equal to r.len, then you need to take r.len plus l.suf. And the same from the left side. Either you take only this answer or the whole array and this answer. So you only need these three numbers. However, now we're stuck with a problem which is operations. We also have queries. During one query, you swap two numbers in this array. And that will result in the fact that we need sometimes to subtract or add on a segment several ones. How to add ones on the segment? If you add ones on a segment, well, you basically, since we know how to merge two segments, we now need to learn how to make an operation if it is applied to the whole array. And on the whole array, it's very easy to add one. Yeah, because now the whole array becomes non-zero array, and you can just say that its suf equals len, its priv equals len, and its ans equals len times len plus 1 over 2. The problem starts when you try to subtract 1, because now if there were no zeros, sometimes they appear. And now it doesn't work. To fix that, let's change the definition of this thing. First of all, we want to store the minimum of the array and the minimum of each segment. So we store minimum of the array. And we also store these three values, but given the fact that we subtracted minimum from the array. So we store four numbers. The first number is the minimum of the segment. And the second three, the third, the fourth, and the third numbers are the following. For example, let's have this array. Let's imagine that we subtracted the minimum from this array. So it became 0, 1, 0, 2. If we did that, what would be the answers to these three questions? And they would be some actual answers. So for example, here suf equals 1, priv equals 0, and ans equals 2. But in this array, these three answers are false. But in case if you know the minimum, if you subtracted the minimum, then these are 3 correct answers. Now you need to fix some operations. You need to, first of all, to learn how to add or subtract 1 to the whole array. But now it's easy. You just subtract or add it to the minimum. How to combine two arrays? First of all, you need to compare the minimum. If the minima are the same, then this procedure is right. But if the minima are not the same, then let's fix that. For example, you had, I don't know, min equals 6, suffix equals 4, prefix equals 3, ans equals, I don't know, I really don't know, 27, and len equals 100. And also you have another array where minimum equals 8, suff equals 5, pref equals 6, ans equals 100, and len equals 200. Well, now you know that this minimum is actually wrong because it is not equal to this minimum. Therefore, if you want to combine these two arrays, then you need to modify the right entry as if the minimum were 6. And if the minimum is 6, then basically suff becomes 100 because all numbers are not equal to the minimum. And pref equals 200, sorry, because it's len. And answer becomes 91100. 20100, I mean. And len equals 200. And only then you can combine them as it is described earlier. So you do it in a segment tree. Also, since this segment tree needs to answer on queries where you make some mass mutations, you need some pushes in your segment tree, or apply some push-free technology. So you can learn that in Codeforces. There are nice blogs which learn you how to do that. And I think that's it. I explained problems from A through F, and problem G was not solved by me. So thank you for watching. Well, before that, I would say that I highly disrespect people who cheated in problem G, because this is not normal, guys. Do not cheat. If you think that it is not visible, this is very visible. This is very visible. I know. You saw how I was solving problem G, and problem G is quite hard. You need a lot to do in this problem. Cheating is bad. Do not do it. Okay, that's it. Thank you.